This is the Waterwheel at Henry Ford's Hayden Mill in Tecumseh, Michigan. I'm Darren, and this is the Industrial Revolution. There are actually quite a few different kinds of water wheels. This one's an overshot wheel, but it's not really the first we want to talk about. Let's talk about the more simple water wheels first, and before we even get to that, let's talk terminology. So here we have a water wheel. It's one of two basic systems for capturing water power. The other one's a turbine. We'll do another video on turbines another time. Upriver from here, we have what's called the mill pond. It's held back by a dam. Mill ponds in more modern dams, and those built especially for hydroelectric, and those built for flood control, a lot of times they're called either a reservoir or an impoundment. With mills, with old plants like this, they're always called a mill pond. Running from the mill pond to the top of the wheel or the inlet of the turbine, that's called a mill race. If it is elevated, like you see here, the elevated part is called a sluice. If it's in a water-filled pressurized pipe, which is the common situation with turbines and especially with newer systems, that pipe is called a penstock. Downriver here, what we have is the tail race. And here the tail race runs under the road and it goes and reconnects with the Raisin River just across the road. Now in the middle of this, we have the wheel, and a few things we can talk about with the wheel. And the most critical part is the head height. Now the water level at the surface is about 3 feet higher than this. It's coming down this, actually to an underground tunnel, and hits this metal distributor here, spreads out across the width of the wheel. And from the top of that sluice to the bottom of the water here, that's called the head. The head determines what kind of power you can generate, what kind of wheel you can use. And there's two kinds of power also that we need to talk about before we go on to the specifics for the wheels. Water's coming down this sluice, it's traveling that direction. It hits this wheel, hits the blades on the wheel. As soon as it hits that, it impacts it and gives the wheel a little kick. That's kinetic energy. The other kind of energy that you have here is called potential energy. Potential energy is when you capture the water in a bucket at the top, and the weight of it pulls this wheel around, and that's potential energy. So between potential energy and kinetic energy, you're converting that into the kinetic energy rotating this wheel, and there's two ways to pull power off it. You have either you can pull power from the hub, which was often done, that's the traditional way to do it, or in this wheel, you can see on the far side, that's toothed, and that's actually, originally there was, and in fact really until a few years ago, there was a gear in that controlled the power going into the building. And on the inside there's a big wheel that ran the overhead belt drive system that ran all the machinery. So that pretty much covers the stuff to run the wheel. Now let's talk about the wheels itself. If you look at this wheel, you see that there are deep buckets. There's two ways to actually capture the water from a water wheel. First way to capture water is with paddles, sometimes called blades. The paddles or blades are sitting here at a right angle to the wheel, spaced across it, and the water hits that, and the kinetic energy turns the wheel. The other way to do it is what this one uses, and that's buckets. Now buckets originally were built, you take those blades that are in here at right angles, and then you put a separate partition down here below that, which lets you capture the water. The problem with those, without it being angled, is and you're up here at the top, all your force is downwards into the axle. You're not really capturing potential energy. By the time you came down here, you'd spilt all the water out because the blade at this point was horizontal. And this is where you have the most potential energy to capture because you're going at right angles to the axle. So by changing the angle, and these ones are set actually about at this angle on the wheel, coming down here, you get almost to the bottom. In fact, the water is not really dumping out there until it's pretty much at the bottom. You lose the last of your water. So you capture a lot more water. Okay, so let's talk about the different types of water wheels. So you have a factory, you're built alongside a river, and you want to set up a water wheel. Okay, so you build your water wheel, you drop it down into the river, and the river flows along. You put blades on it, water flows along, hits the blade, spins your wheel, you pull power off your axle, everything's great. And that's called a stream wheel. Stream wheels were not really common. We'll come to why in a second. Stream wheels, as I mentioned, do use blades. Stream wheels capture kinetic energy. They do not capture potential energy at all. The blades really can't capture potential energy. Now, the problem you have is, let's say you build this wheel and you put it into the stream and you build it in the spring at high water because you don't want it to flood. Okay, now summer comes, your water level drops, your wheel's high and dry, no more power. Okay, that's not going to work real well. So you build it down low in the summer. Water comes up. Now you're spending, as your blades go down, now you're pushing this water down instead of actually doing any useful work. Over here, you're lifting the water back up instead of doing useful work. Again, you're wasting most of that energy. So that led to the undershot wheel. And the undershot wheel, you lift the wheel up a little bit. You lift the water so it's just above high water mark. So your river, no matter how high the water is, your river water never touches it. And then you go back upstream a little bit and you build, coming downstream, you build in a bit of a mill race. It's elevated, and maybe that's up 2-3 feet. And you bring the mill race in and you hit the bottom of the wheel, same place you would have hit it for a stream, and that spins the wheel. But because it's elevated, no matter what happens to your water level, you always spin the wheel the same way. And you can adjust the water flow by opening and closing a gate on that mill race. That's an undershot wheel. Undershot wheels were pretty common. For an undershot wheel, again, it's only kinetic energy, which is the speed your water's flowing. It does not capture any potential energy. And these are ideal. So the stream wheels, you could work with 0 head height. The undershot wheels, you really only needed 2-3 feet of head height, if that. You could get away with a little less if you needed to. And that would be fine for an undershot wheel. So if all you had, if you have a stream that's like flowing, decent flow, but not really a lot of drop, instead of building a mile-long mill race going upriver, you could actually just set this up as an undershot wheel, and maybe you only have to build your mill race 50 or 100 feet upriver to get enough run down there. Okay, well, what if you have something like this? What if you have a high head? So head height, remember, is from the inlet to your water source all the way to the bottom. So here you have a high head. This wheel is probably 20 feet in diameter. So with a high head, you can do an overshot wheel. Now this wheel is barely being fed by water. In fact, the owner of the building stopped by and we were talking about it earlier. And really, it does cut down a lot on the wear and tear. It cuts down on the wear on the bearings, and it's not powering anything, so it doesn't really need any more water. But if you have a high head, then you can do an overshot wheel. You put buckets on the inside of the wheel instead of the blades. If you did blades and you hit an overshot wheel, and there are some built like this, the water would hit the blades and start spinning the wheel and then just splash out, and you're not capturing potential energy. With the buckets, the water hits it and it's captured by the blade, by the bucket, and moves around. And that lets you capture both the kinetic energy and the potential energy. Now there's a problem with this also. And the problem is, although this is not running real fast right now, you aren't really splashing any water everywhere. If this got opened up to actually provide good power, you'd be seeing a lot of water splashing out of here. And the water that splashes out, you're not using. You get the kinetic energy off of it, but you don't get the potential energy. And potential energy has a lot more power than an overshot wheel. So then you move to the next idea, which is called the back wheel. In the back wheel, you take this wheel, you take it out, and you turn it around. So it's facing the opposite direction. The buckets are set so it'll spin this way. You close the end of the sluice and you cut holes in the back of the sluice so that the water comes down onto the back of the wheel instead of the front. Water comes down the sluice, hits the end of the sluice, you've lost all of your kinetic energy. Water then drops straight down onto the wheel just behind the axle and fills those buckets. You're not doing a lot of splashing, you're not like losing water over the sides, you're not shooting water over the front. Those can actually be more efficient. So now it rotates the other direction. And again, with the buckets in here, it keeps the water almost all the way to the bottom. Very efficient way to run water. It does require a high head, just like the overshot wheel requires a high head. You're not capturing any kinetic energy at all. You're using entirely potential energy. Now, generally, you don't care which way the wheels turn. And there is something in between the overshot and the undershot, and that's actually called the breastshot wheel. And for that, you have sort of a medium head. Your head comes in around the point of the axle, or a little above, a little below where your axle is. And the water comes in and hits the angled buckets and pulls it down from the back. Now, that lets you use a bigger wheel. So if you have a medium head, let's say you have a 5, 6, 8, 10 foot high head, kind of low for an overshot wheel, but it works great for a breastshot wheel. You don't want to throw away that energy by just doing an undershot, so you do the breastshot, but you want a bigger wheel. So the breastshot comes into the back, slams into the wheel, you don't get anything from kinetic energy, but you fill those buckets and pull it down on the back. With the overshot, your buckets are full almost all the way around, assuming you're doing these sharply angled buckets. With an undershot, your buckets are full about halfway around. So you don't get as much power for the same amount of water, but it's still pretty good. It's still better than an undershot would run. So let's say you have a really big head. Let's say you have 100 feet. Okay, so you build a 100-foot overshot wheel, and everything's great. You're getting so much power you don't know what to do. Except, especially when you're building in wood, your wheel's going to collapse from the weight. You can't rotate a 100-foot diameter wheel filled with water. That thing weighs tons. The thing will just collapse on you. The other thing is, at that point, it's probably more than what you actually want. So you have a couple of options here. One way to do it, and we have drawings and ruins from an ancient site that actually just changed water wheels coming down. So it's overshot wheel. There's maybe a 10 or 20 foot diameter. And the tail race from here is the mill race for the second one, another water wheel, another 20 feet. Tail race, it becomes the mill race, another 20 feet, and you can just chain them coming down. And that works great. If you're doing something like a grist mill, for example, you don't need massive amounts of power, but with all these wheels, you can run more and more stones. And running more stones lets you grind more, and if you have to shut down one for maintenance, you just put the brakes on the wheel, let the water dump down past it. You're still running all of your other ones efficiently, whereas if you had one giant wheel, even if you're able to support it, that one giant wheel, if you had to shut that down for any reason, your entire operation will be shut down. But nowadays, we're running in steel here, so why not just take the steel and build that 100-foot diameter wheel? Well, we could, and if you had enough water to power it, we could do that and it'd work. It's not actually ideal. The reason it's not really ideal, the reason you don't see 100-foot diameter wheels running over at Hoover Dam or whatever, the smaller wheel, you get into like the 10, this one I said about 20 feet. That's kind of about as big as it makes sense. You get much bigger than that, and it takes so much water to turn them, and you're starting to lose water as they drop. And your efficiency, after you pass a certain point, you've lost so much efficiency, you'd be better off running a couple smaller ones. So that really impacts the maximum size of wheels. That's why you'll rarely see much bigger than this one. So there is one other kind of wheel I want to talk about, and that is actually the horizontal water wheel. Chances are you've never seen one. These have been around for over 2,000 years, and the horizontal wheels were actually developed about the same time. The horizontal wheels, unlike these, are small. They can be a foot, foot and a half, maybe 2 feet in diameter. They're very useful where you have very low water flow. The way they're set up is that you have usually a small mountain stream feeds water. You don't need much water for them. The blades are set at a 45-degree angle around the wheel. The water from a sharply sloped sluice comes in, hits that wheel on one side and makes a turn. There's a simple shaft up to a small millstone on top for grinding wheat. Then you have the non-moving stone on top of that. This was actually something that was not useful really commercially. It was useful for the small family farm, the very small operation, where you're not actually working with just massive amounts of wheat. You're looking at enough for a household. And if you think about it, before these wheels were available, what you were looking at was hand grinding, probably for a couple hours a day, all of your grain into flour. Now, once you've done that for the day, then you bake the bread, and people at the time lived mostly on bread. And then the next day you do it again. With these little horizontal water wheels, you could actually go out and spend an hour or two one day, and you had your flour for the month. So far better to do it that way. It worked great, not scalable. It couldn't be scaled, but if you gave a farmer at the time a diagram of how this thing worked, they could build it. These are not complex at all. The stones were very manageable. You're looking at 100, 200 pounds tops for the millstones. So this is something that pretty much any farmer at the time could build. And then they could get rid of that couple hours a day of very manual, very hard labor of grinding their wheat. And they could then make that a very simple process. Now, I mentioned you didn't see a lot of them, but the one I have video here, that's from the early 1900s. And they were still used because they still worked, quite simply. And they were very usable in places that had, like fast-moving mountain streams where you had a lot of drop in the stream, but you didn't have real high water volume. For water wheels, you kind of need more water volume. I mentioned you have the drop, the head height. The other major factor is how much water you have. This one's running very minimal water. If you get up close to it here, you can see these buckets barely have anything in them. So it's not really able to produce much more power than this. I could probably grab this and stop the wheel with my hands right now. But if this thing were running at full speed, if the sluice were open, wide open all the way, I would not be able to stop this. I wouldn't even try it. So that's the difference. Now, vertical wheels were scaled up, they were chained, had lots of use. Horizontal wheels never were, but they were still used. And the other critical thing with horizontal wheels is that's what eventually evolved into the turbines. And the reason you don't see water wheels today is because we're using turbines. But despite that fact, these wheels, this was the beginning, really. Water wheels finally let us move from human and animal power to mechanical power. And that's why this is the Industrial Revolution. So I do need your help to keep this channel going. And there's 4 main ways you can help me out. The first 3 of them are completely free. First, if you enjoyed the video, please hit like. It costs you nothing, it's 1 click, and that tells YouTube, hey, this video is worth watching, show it to more people. Second way you can help out is to subscribe to the channel. That will notify you whenever a new video comes out. Also, again, that tells YouTube, hey, this whole channel's worth watching. Show this to people. That's going to increase my viewership. Third thing you can do to help is comment. Comments with more than 2 or 3 words on YouTube videos. That's the most powerful thing you can do to help any YouTube creator to grow their audience. And finally, I do have a Patreon page I'm just getting set up. It's over at patreon.com/industrialrevolution. There's a link down in the description. If you'd help out there, that'd be great. That's just a few bucks a month. We're just starting out, but once we start to build a community, I'm hoping to be able to set up regular monthly or quarterly online chats so we can actually have conversations with our community members. Anyway, thanks for watching the video, and I look forward to seeing you at the next one.